Hey guys, welcome to my video, and this is for UHS MDCAT students who will be appearing in the entry test. And this video is made specifically for A-level students who are going to find difficult to transition to the FSC course book in order to appear. And in this I will be doing a lot of questions from the organic topic, because the MCQs that are given over there, they are very different from the sort of MCQs that are likely to be asked at A-levels, and the sort of content that is often tested is different as well. So it's a whole new world for us. So hopefully this video will help you guys acclimatize. So you need to consider the following structure of halothane, and the correct name of halothane according to IUPAC is: number 1, you should be aware what halothane is. Halothane is basically an anesthetic and is one of the more important halogen compounds, and it is perhaps the only anesthetic that contains a bromine atom. So this isn't all that much of a biggie. We have 2 carbon. On one of them we have a Br attachment, we have a Cl attachment, we have 3 F attachment. You should know that all of the halo attachments have the same priority, and that when we have numerous such groups attached and have the same priority, we write their names in order of alphabetical order. So let's see. They've given an example: 1 chloro, 1 bromo. Not true, not alphabetical. Fluoro, then chloro, again wrong. But this is all right. 2 bromo, 2 chloro, 1 1 1 trifluoroethane. This is it, because this is the only one in which it's written in alphabetical order: B followed by C, C followed by F. Otherwise, chloro-bromo and fluoro attachment groups have the same priority when it comes to naming. And if we have the same attachment on the same carbon, then we will have to write the attachment position separately for each attachment, even if it happens to be on the same. And we also have to use some sort of a prefix. In this case, try, and the prefix has no influence on the order. When ethanol is formed with ethanoic acid in the presence of concentrated H2SO4, which acts as a catalyst, an ester ethyl ethanoate is formed. So what happens during this reaction? This is simple esterification. Is the alcohol reduced? Is the OH bond in ethanoic acid broken? Is the OH bond in ethanol broken? Is the acid oxidized? Now surprisingly, you would expect that it is the OH bond in the ethanoic acid that would be broken, so releasing an H and forming a bond, but it is in fact the OH bond in ethanol that is broken, and the CO bond in ethanoic acid that is broken. This is something you will have to find in the book. They have actually given quite an explanation on this even, so it's not something to be confused over. So Teflon is used as a non-stick coating for cooking pans. So what it is, a polymer of. Now you need to know some background of Teflon as well. So it's made up of a monomer which has 2 carbons and 4 fluorine attachments, and it's a pretty valuable plastic, right? Because it's really corrosion resistant, so it's often used for the insulation of wiring. It's also used in the parts of machinery that need to be corrosion resistant. But if we talk from a colloquial point of view, You will have heard Teflon most often in association with its role as non-stick coating on pans and stuff. And since we're at this point anyways, I'll have you know there's this topic, the halogens and noble gases, and they have given some properties of the halogens and the noble gases in separate topics. These are very important. And I'm reading a paragraph from over here. Fluorine is used to prepare Teflon, right? They've given the monomer CF2CF2. It is a polymerized tetrafluoroethylene compound. It is a valuable plastic which resists the action of oxidants, acids, and of alkalis, right? So Teflon is basically, it's resistant, it is not susceptible to attack by acids, even alkalis, or any form of oxidation. And the corrosion-proof parts of machinery are made of it, and is also used for coating electrical wiring. Teflon is also used as a non-stick coating for cooking pans. That's it. Now, another thing is they have given halothane in the book, actually right on the same page in which they're given the properties of Teflon. So they may ask you what is the correct formula. So you need to remember that it contains 2 carbon, which is important. One of the carbons is attached to 3 fluorine. The other one is attached to 1 bromine and 1 chlorine. So again, you would be confused because not this sort of question that can come up in A levels. We aren't all that heavy on theory, but you have to be careful on each and every stuff that is written. They may have given the common name of compound. It may have been somewhere in the corner or in the tidbits. They may give that. So you need to be really careful and really thorough. So is the answer ethylene? Ethylene is basically just ethene. Again, this is more of a common name than anything else, a bit outdated, so you might be unfamiliar. This is ethylene, and no, this is not the monomer for Teflon. It is the monomer for what do we call that? Polyethylene. Styrene is also different. Styrene is the one for, I believe, polystyrene, and I don't want to mislead you, but you should, so because I don't really remember at the moment. But styrene, this is actually really important, something you should know as well, mainly because polystyrene comes up in the macromolecules topic, and we have 3 marks coming from that, 3 MCQs coming from that. And now I've checked so I can be sure. The monomer for styrene is, and over here we have a benzene attachment, C6H5, and with the help of a catalyst we can make a polystyrene molecule out of this monomer. And how is polystyrene important? Well, we know we use polystyrene as packing material. We also know that we use polystyrene to make bottles, and we also use it to make certain toys. You might be a bit unfamiliar with this concept, but there is a huge variety of stuff we can do with a lot of plastics which we might be unfamiliar with. And you would know that a lot of our takeout comes in certain containers that are disposable. Those are made up of polystyrene as well. So food containers, bottles, especially cosmetic bottles, toys, and packing material. So what about chlorofluoromethane? Well, that's not even a monomer because that does not have any double group to work with. So yep, tetrafluoroethylene, and that is basically tetrafluoroethane, for those of you who are not familiar with the naming. So which of the following alkyl halides shows pure Sn1 mechanism reaction? Now what is the Sn1? You know these. Sn1 is the one in which there is only one molecule attachment at a time. So it's composed of two separate steps, and the first one is the rate determining step, in which a carbocation is formed, which is attacked by a nucleophile in the other step to form the product. Right, and Sn1 mechanisms, they are usually preferred by tertiary alkyl halides, and because they're saying purely, and sometimes Sn1 is showed by secondary as well, but because they have mentioned purely, so let's look for that. Interesting. This is secondary, can show occasionally but not definitely for certain. Answer is B. So you need to consider the following structural formula. So what is the correct name according to IUPAC? Again, naming. Number one, you have to identify the longest carbon chain. 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5. So it's this one. Now we have two substituents. We have this portion over here, and we have this portion over here. Now, as far as I know, there isn't any difference in priority when it comes to the alkyl part or the halo parts. They're basically the same in terms of priority, but we tend to start naming from that point, which gives the smaller number to the first substituent. So we can start from here. 1, 2, 3, 4, 5, 6. In total 6. So the parent will contain hexane. All of them contain that. 2 chloro and 4 methyl. This is wrong because naming. So C before M, alphabetical. This is wrong. We have to consider these. So it's 2 chloro 3 methyl, definitely wrong. 3 chloro 2 methyl, doesn't make any sense, but this is all right. 2 chloro 4 methyl hexane. Now you have to be a bit aware of the priority stuff. It's easy when you're just having the halo and the alkyl substituents, but sometimes more complicated come up. And there's this topic in the, unfortunately with the FSC book, stuff is a bit haphazard, so it's a bit difficult to maneuver if you're unaware or unfamiliar with the books. So in 160, on page 169, we have the topic on aromatic compounds, and somewhere in the naming, which is actually not included, the naming of the benzene parts, in the UHS they have given the coordination, actually the sequence of priority, and it goes something like this. The most important one is the carboxylic, followed by the cyano, followed by the ketone, followed by the aldehyde, and after that I think there is the alcohol, and in the last we have NH2. But don't worry, I will tell you the exact order in case I missed something out. These were the more important ones, however. Yep, most important, C double bond OH, followed by C triple bond N, followed by aldehyde. My apologies, I may have said ketone first, followed by ketone, followed by OH, followed by NH2. And one thing I missed out is that after NH2 we have this. So any sort of functional group other than OH, that is an O with an attachment that is not H, that will be of less priority than NH2, but more priority compared to a simple alkyl attachment. So this can be, say, an ether attachment or something. This is literally it. So these namings, these orders are different, and unfortunately it's also difficult to find because it's just randomly written in one of the nomenclatures from one of the chapters and not to be found anywhere else, but fairly important. So one thing to remember, which I messed up on, is that the aldehyde group has more priority than the ketone, which can be a bit surprising. And another thing that is really important is that the OH part has more priority than the NH2, and that the alkyl has less priority than the OR formation. So the alkyl halides, they show Sn1 mechanism reaction. This mechanism has all of the following characteristic features except Sn1. Again, it is a two-step reaction. The first step happens to be the rate determining step. The other one is the fast step and has no bearing on the rate of the reaction. So it is a two-step mechanism. Yes, it is unimolecular and first order. Well, it is unimolecular in the sense that the rate determining step, the one that actually has an influence on the rate, contains just one molecule. So even though there are two molecules in total, it is unimolecular in the case of rates. So this is all right. It shows 50% inversion and 50% retention. Now this is something that is unfamiliar to A-level students, these terminologies, but you do know this, you just don't know what they're called. So when we have a carbo-cation formation, right, we have read this and it has come up in questions that the nucleophile can attack from either side equivalently, right? So if it attacks from the same side that nucleophile left, there will be retention, and if it attacks and attaches to the opposite side, there will be inversion. So 50% inversion and 50% retention, absolutely correct. Now if this was Sn2, because it can only attack from the opposite side to the side that has the nucleophile, there will always be inversion. So 100% inversion in Sn2. That only leaves the first part. The rate of the reaction is favored by the non-polar solvent. You do tend to use water or alcohol, so that does not make much of any sense. So the A is incorrect. So what is the correct name of the following aromatic? And here's the tough part coming up, because this is common name. So we do know what it is called. We know this is a phenol, so the base name is phenol because that is the important part. And then we have attachment at these points. So it's 2,4,6 trinitrophenol, but what's it called colloquially? Nitrophenol? Nope. Benzoic acid? Obviously not, because that simply has a C double bond OH attachment. Is it malonic acid or is it picric acid? What's malonic acid? That is a question that you can get. Now, malonic acid is actually a dicarboxylic acid, and it's like this actually. So it's this one. So it's obviously not this. So that leaves picric acid, and yes, picric acid is indeed the common name we are looking for. So in my opinion, there are a couple of other common names as well that are vastly important. One being carbolic acid. Now this messed me up the first time I saw it in a question. I was like, what is carbolic acid? Simply put, carbolic acid is an archaic name for phenol. Yep, I guess you didn't see that coming either. And that was mentioned somewhere, I guess, except I don't remember. I didn't really pay that much attention to the secondary names, but they were asked. Now the alkanes and the alkenes, they have these subsidiary names, the olefins and the paraffins. And the paraffin is for the alkanes and the olefins are used for the alkenes. And now you'd be confused. You'd be like, where was this? Was even part of the UHS MDCAT syllabus? Well, it wasn't quite written. But they do ask the physical properties and some of these general properties of the groups, even though it's not really mentioned in the syllabus. And I guess that is all right. I suppose it's really annoying, but can't argue with this sort of thing. So if you take out the aliphatic hydrocarbon topic, it's written at the top of the portion where alkane starts, alkanes or paraffins. So yes, paraffin is a secondary name, and the same for the alkanes topic. It's written alkanes, well, not, and olefin isn't written next to it, but it is written right in the second line that they're also known as the olefins. Now there are some other ones that are important. They're not quite coming to me right now. Well, there's acetone, and there is acetaldehyde, there is formaldehyde, there is stuff like that. So which of the following alkyl halides has greater boiling point? Now that is a good question. Well, the alkyl portion is the same. So what is the boiling point going to be dependent on? Well, it tends to be dependent on the intermolecular forces. So which one? A, B, C or D? Well, if we were going only on variable forces, we would have said B, because iodine is by far the largest molecule, has the greatest number of protons, the greatest number of electrons, and so the most powerful London dispersion forces. However, we're going to go with A on this one because CH3F, no, my apologies, I made a mistake. It's indeed B, because it's the attachment of C is with F and not H with F. In that case, we would have the really sought after, the really legendary hydrogen bonds that have so great an influence that they literally tear apart all other forces in their bed. Now there's this in the starting chapters, we have the intermolecular forces, and these often come up not as much in themselves but often come up in the organics topic. So something you need to really read carefully. It's page 81, I believe, and it's the first book. Hopefully all of you would have bought the Punjab textbooks, whereas the other ones that the questions are going to come from. So we have the dipole forces, right? It's when we have both the molecules have dipoles and there is an interaction between them, right? And there, a lot of the stuff is the same in this topic, but some stuff is new. For example, they have told us that the dipole forces are just 1% as strong as a covalent bond. Well, you would have realized that there is a big difference in the strength of the intermolecular and the ontomolecular forces. You would not have known the value. If they said 1% as strong or 10%, you would be divided. You might go for 10. That seems a bit more sensible had you not looked at the value. So you need to be careful because there are some new stuff, especially in terms of numerical stuff, which we don't really pay that much attention to anyways, but that comes up the most frequently. So I'll repeat, a dipole force is about 1% as strong as a typical covalent bond. So you'd probably already know what the strength of dipole forces depend on. It's more largely dependent on the electronegativity difference between the bonded atoms, and also is dependent on the distance between the molecules. So two factors: the electronegativity difference. The bigger the difference, the stronger the dipole forces. So the more electronegative one end and the more electropositive the other end, the stronger the bond between them, the greater the electronegativity difference. However, distance has a huge impact on forces. Even a short amount of change in distance greatly reduces the force. So if you know this value, that is the reason why why the forces are very weak in the gas phase, even though we often tend to have a lot of dipole forces. And the reason for that is that the distance between molecules in the gaseous phase is so huge that the forces are made nearly negligible. And this is literally the basis of the ideal gas theory and stuff. How you would expect that these same forces in the liquid phase will have a huge impact. And another thing is, you need to know what a thermodynamic parameter are. They mention this again and again, and initially I had a bit of trouble understanding. I thought they may have something to do with heat and stuff, and I was close to the mark, but I was still not really certain about it. So thermodynamic parameters are the melting point, the boiling point, the heats of vaporization, that is the amount of heat needed to change from the liquid to the gaseous phase, etc. in the heat of sublimation. That is the amount of heat needed to change directly from the solid, from the solid to the, no, I was right the first time around. Sublimation is when we go directly from solid to gaseous phase and effectively skip the liquid phase, right? None of the new stuff they've told us is that dipole-induced dipole forces, they are called as Debye forces, right? And we had a bit of fun with this Debye forces because I thought it was really crazy how they were giving everything secondary names, while we literally had trouble remembering the slightest things at A-level. It's not that our concepts were bad, we just didn't care about all of this stuff. But it's not all useless, you would think. I found initially that I thought this was all useless, learning the product table, not all of it, just a lot of it. But then afterwards I realized that there were certain advantages to it. I thought that a lot of stuff, you have concepts, but you don't have the product table, and at that moment you're not able to use any of that concept. So if you have a bit of stuff memorized, it's really helpful. And hopefully you remember what a London dispersion forces, because I think this name was mentioned at A-levels. So that is basically the one in which there isn't any polarity to speak of, and it's just instantaneous dipole-induced dipole forces. Right? And you should also know that they're very significant in non-polar molecules like chlorine, H2, and the noble gases. Also, you should be aware of how these come into being. So if we consider the helium molecule, we have two helium, so the electrons of one atom, they are effectively influencing the moving electrons of the other atom. So the electrons are repelling and they tend to stay as far apart as possible. And when the electrons of one atom come close to the electron of the other atom, they are pushed away from each other because same charge repulsion. And because of this repulsion, there is the creation of dipole. And this dipole is not a permanent one, it's temporary, it lasts instantaneously, hence the name. And the result is that at any moment, the electron density of the atom is no more symmetrical. More negative on one side, more positive on the other. And at that particular moment, the helium atom is effectively a dipole. So these are all the new stuff that was from this topic. I wanted to give you a summary so you wouldn't be troubled about it. So onwards to the next. In tertiary alkyl halide, the halogen atom is attached to a carbon which is further attached with how many H atoms? This is easy. It is not attached to any hydrogen atom. So the alkyl halides are considered to be very reactive compounds towards nucleophiles because of what reason? Now when we talk about an alkyl halide, the carbon is the part that is attached to the halogen, and we know the halogen to be considerably more electronegative, and so it sort of siphons off a lot of the carbon's electronegativity and sort of leaves it with a partial positive charge. And you should know that anything that has a partial positive charge or a free or a full positive charge has the ability to act as an electrophile because it is deficient, and so it's pretty much into lobbing electrons. So yes, a reason can be that they have an electrophilic carbon, and the one carbon that is considered electrophilic is the one to which the halogen is attached. And I believe that is the carbon we would refer to as the alpha carbon. They have an electrophilic carbon and a good leaving group. Well, they can have a good leaving group, but not all of the nucleophiles or all of the attachments can be considered as a leaving group. So when we're talking about a leaving group with respect to an organic compound, it's usually that group or that single atom which is replaced, that is effectively substituted. So in alkyl halides, a leaving group will be in relation to its nucleophilic substitution, and leaving groups are basically the halogens. But are all of the halogens considered good leaving groups? Well, they're not usually considered as such. But yes, they are good leaving groups. Chlorine, bromine, fluorine, and iodine are good leaving groups. The special thing about iodine is that it's good at both. It's good at being a nucleophile, and it's also good at being a leaving group. So it's good at being this thing that is being replaced, and good at being the thing that is replacing some other atom in some other compound. So B can definitely be the answer. They have a nucleophilic carbon? No, that is incorrect. D, they have an electrophilic carbon and a bad leaving group. That is not true. I would go with B. So when we talk about in terms of good leaving groups and good or bad leaving groups, usually the good leaving groups are the single molecules, like Cl, bromine, and iodine is a single molecule, whereas something like amine, NH2, or OH is a bad leaving group. And the way I remember is that it's because, or it can be because it's a group that is made up of more than one atom. And if you're curious about this has been mentioned in the book in the alkyl halides topic, page number 194. Unfortunately, they have not given much of any explanatory detail, but it's definitely written. They've given the names. Leaving group. And they've also explained what is a leaving group. Something is called leaving group because it departs with an unshared pair of electrons, and this is important whenever something is being replaced by a nucleophile. The one that is leaving is a nucleophile as well as the one that is replacing it, and because it is a nucleophile, it's going to take two of the electrons that form the bond with the carbon with it when it departs. Right? If you wish an SN reaction to proceed in the forward direction, the incoming nucleophile needs to be stronger than the departing one. That should be obvious enough to understand. Now they've given examples. Cl minus, Br minus, I minus, and HSO4 minus. Now this is an exception because it's not made up of just one, right, molecule, but it's a good leaving group. So you're going to have to find some other way to memorize this. And the poor leaving groups are the OH, the NH2, and they've given another. I guess it's a good idea to put the lone pairs over here to sort of like emphasize their existence. And another option can be OR, and I is basically usually an alkyl portion. So this is a good leaving group along with Cl minus, Pr minus, I minus. These are bad leaving groups. And they've also written that iodine is very special in that it is good at being both. And eventually it was when I could do something good, because I find that it is the most underappreciated of the halogens often. When we talk, so which of the following is not a nucleophile? This is obvious, BF3, because a nucleophile needs to be able to donate an electron, and BF3 is already deficient. So alkyl halides show which of the following types of reaction: nucleophilic substitution, electrophilic substitution, nucleophilic addition, or oxidation reduction. So the answer is nucleophilic substitution. Obviously, when an alkyl halide is treated with KCN followed by hydrolysis, what is the product? Easy. With KCN, under the condition of alcoholic KCN, we have a simple nucleophilic substitution, and what we end up with is a nitrile. And when a nitrile is acid hydrolyzed, the product that we obtain is a carboxylic acid. Now, another new thing about acid hydrolysis that we A-level students were unaware of is that it's actually a two-step process. And another important thing, so if we have this over here and we put in the ingredients, initially we will have a partial hydrolysis, and the result of that will be surprisingly an imide. Right? So how that comes is because obviously when we are doing acid hydrolysis, the acid has what in it? So what is an H plus? H3O plus. So what happens is that we get one of the O's and we get one of the H's, right? In the next one, we get effectively another O from one of the H2's. Right? So another H2O effectively comes to the rescue. And we take one of the O's, and this part is sort of like it has nothing more to do. So we have NH2, NH2. In addition to that, we have one H because one of the H has been attached over here. So we basically get NH3. But because NH3 is alkaline and effectively we are doing this in an acid portion. So for example, if this was say HCl, HCl was a mineral acid being used, we would have gotten NH4Cl. And this one has actually been repeated in a couple of different chapters, but I still think this is something important. Right. So which of the following isomeric alkyl halides has the least boiling point? So all of these are isomers of each other, so they have the same molecular mass, and so their boiling point is going to be dependent on their arrangement. The one with the least boiling point will have the most branching, because branching effectively reduces the surface area. We know this from A levels, nothing new. So which of the following compound is used as a refrigerant? Definitely not CCl4, because this is tetrachloromethane. You do not use that as a refrigerant. What about CH, Cl3? Nope. What about CH2Cl2? No. What about this? Definitely. Because this is what you call a freon, and a freon is a low molecular mass fluorocompound which often has, almost always have fluorine with it. And what do we use freon for? We use freon for a lot of stuff. We use it in refrigerants, and in addition to their usage in refrigerants, we also make use of them as aerosol propellants. And what I used the term to describe them as being low molecular mass, that was really important. So no problem, this is also written in the halogens and the noble gases topic. They have mentioned it, and this is an important question. And freon is the commercial name of low molecular mass fluorochlorocarbons. So they need to have both fluorine and carbon. Examples being CCl2F2, and this is the one they've given, and another example is CClF3, and we use these as both refrigerants and as aerosol propellants. So you need to consider the following reaction. So which product may be formed? This is the reaction between an alcohol and PCl5. Obviously what we're going to get is a substitution. We're going to get an alkyl halide. So both of these contain, actually all of them contain that. But in addition to that, we're going to get a couple of other stuff as well. Namely, we're going to get POCl3 and we're going to get HCl. And we know this, we have done this. It's also written in the FSA book. So alkyl halides show elimination. So what is the incorrect statement about even elimination? The elimination also has two possible mechanisms, and this is something A-level students don't know. However, an even has literally the same sort of properties that Sn1 has. Na2 has the same sort of properties that Sn2 has, and this is just what you need to know. You don't need to go into details. So is it two-step? Is Sn1 two-step? It most certainly is. So this is correct. So is rate determining step first order kinetic? Is it for Sn1? Yep. It is dependent on the strength of the attacking nucleophile. Actually no, that is true for Sn2 and E2, but not for E1 and Sn1. But let's put this in reserve. Let's say the last one. E1 elimination involves dehydrohalogenation. Yes, of tertiary alkyl halides. Is that true to some extent about Sn1? Yes, Sn1 is for tertiary. So the wrong one is C. So fermentation is a biological process which occurs in the presence of certain enzymes secreted by yeast and other microorganisms. All of the following are essential conditions for the fermentation except. Let's do this one later because again this isn't really part of the syllabus, but some of the loopholes, they sometimes transition into territory and grab stuff from surrounding topics which they don't really mention in the textbook. Not in the textbook, in the syllabus. They're very infrequent, but they do ask. So these two we'll leave for the end. What is the structure of the alcohol which on oxidation gives a ketone? We need a secondary alcohol for that. This one, nope. It's primary. What about this one? It's another problem in and of itself. This one, nope. What about this one? This one has an H over here, a CH over here, and OH over here. Yes, this one will give because this has a secondary alcohol. Alcohol can be denatured by adding the following except. 10% methanol. Well, we do know that is what they actually do. Example, pyridine, acetone, or ethanol. Pyridine is basically this base they have mentioned, and actually you need to know the structural formula of this one as well. It's written in the first chapter. From the organic compounds and substituents, don't pay attention. So this is the structural formula of pyridine. So it has 4 carbons and 1 N, and this is what you call a heterocyclic compound. We're going to revisit this next. Consider the following structure. What is the correct name according to IUPAC? OH has definite priority, so we start naming from this end. 1, 2, 3, 4, 5. So we have 5 carbons, so that's pentan, and the parent name should include OH. So pentanol, and it's 1 pentanol, and the chlorine is on carbon number 4. So it's 4 chloro, 1 pentanol. It's wrong to write hydroxy over here, not only because they have not mentioned the chlorine, also because we only use hydroxy as a prefix when the alcohol is part of a compound which has a higher priority group, like the carboxylic. The general formula of an alcohol, that's easy. You should know that if you compare an alcohol and an alkane, they literally have the same, except in addition to one of the H's, we have an O. So which one? It should be CnH2n plus 2O. So which of the following alcohols is least soluble in water? So what is the solubility of alcohols dependent on? 2 factors, hydrogen bonding and the length of the hydrocarbon chain. So the smaller the hydrocarbon chain, the more soluble. They're asking for the least soluble, I believe. So methanol, propanol, ethanol, and butanol. So this one was fairly simple. As I've already mentioned, oftentimes they ask about physical characteristics in a indirect manner, even though it's not exactly written over there. So it's a good idea to have this brief look over all of the physical properties of in the organic. It's not really that big, just have to read it like once, really carefully. Other important thing is that the alcohol group is quite closely related to the ethers and to water. So page 2016, we have the physical properties. So they have described the lower alcohols as, generally speaking, colorless. So we're talking about lower ones. So they're generally speaking colorless, and that's something we know from our lab work. They are also, generally speaking, really toxic. So I wouldn't, we have this thing with alcohol going, but yep, the ones we're talking about are not the drinks. They have not been processed in any such manner, and they are generally toxic. Talking about the lower OHs at the moment, as we know, there will be changes in the properties as the hydrocarbon chain gets bigger and bigger. So they're readily soluble in water, but solubility decreases in higher alcohols, and this is important. And the solubility is due to hydrogen bonding, which is prominent in lower alcohols but diminishes in higher alcohols. This is important. And the melting and the boiling points of alcohols are higher than that of corresponding alkanes. Methyl alcohol and ethyl alcohol are liquids, whereas methane and ethane are gases. This is an important thing to understand. This is due to hydrogen bonding present in alcohols but absent in the alkanes. So this is a comparison. CH4 and C2H6. These are the first two members of the alkene family. They're both gases. However, the first two members of the alcohol family, and that is methanol and ethanol, they're both liquids, and that is because they have this hydrogen bonding, which really has an influence on their bonding ability, on their intermolecular forces. So as I've said, really careful about the physical properties. They're not really specified, so to speak, in the syllabus, but it's something they can often ask. So I'll repeat. Noble alcohols are generally colorless, toxic, and they have this characteristic sweet smell, and they have a burning taste if you have a dead fish. Readily soluble, but solubility falls. Right? So I wouldn't suggest that you confirm the burning taste, but the sweet smell it's almost sickly sweet. If you ever use spirit or alcohol, you would find that it's so sweet, it almost makes you nauseous if you're exposed to it for longer than you have to. And it's really volatile too, so please don't leave the bottle open after you're done with it. You're gonna get a beating, metaphorically speaking, from your teacher or your mother or your father when they find out. So back to what we were discussing. Question number 81. When CH3 CH2OH is oxidized in the presence of A2CO2O7 and H2SO4, what is the final product? Now this is a primary alcohol, and they're asking for the final product. So it can either be a carboxylic acid or an aldehyde. This is an ester, this is a ketone, and this is, well, a carboxylic acid, but not the right one, because this has just one carbon, whereas this is a 2-carbon alcohol. Easy. So which of the following tests can help us distinguish between primary, secondary, and tertiary? Tolerance is not effective on alcohols and will have no effect, will not successfully oxidize any of them. Bayes test is basically alkaline KMnO4, and it's pretty dilute, about 1%, and it's not that much of a good oxidizing agent. So distinction is difficult. Can it distinguish a primary from a secondary? No. Well, it can likely distinguish a tertiary from these two, but not the other way around. An iodoform test can successfully, in most cases, in a lot of cases, distinguish a secondary from a primary or a tertiary. If the OH is on a carbon which is adjacent to a metal, then it is a good idea. It can also be, it is also characteristic for one particular primary alcohol, that is ethanol, and will not do so for any of the, or likely any of the tertiary. So the answer is actually the Lucas test, which is not mentioned as being part of the syllabus and is unlikely to come up, but it's the obvious answer because all of the others are pretty iffy. None of them would 100% tell us the answer. The alcohols topic is actually pretty easy comparing to your A-level. Work might even be easier, even less material heavy, so to speak. And it's great because we're getting like 4 MCQs from it. So easy marks, but don't take it lightly. Those are important marks, and you have to be really careful that you don't lose any of them because of negligence. And Lucas test can be found pretty easily. over here, yep, it's used for distinction between primary, secondary and tertiary. And what is the Lucas test? It's basically when you react with concentrated HCl in anhydrous zinc chloride, and you would get an oily layer of alkyl halide formation, and there would be multiple such layers and they would separate out because they would be immiscible. Now tertiary alcohols would form an oily layer immediately. Secondary alcohol would take about 5 to 10 minutes, and primary will only form a layer on heating. So this is the Lucas test. Primary alcohols give aldehydes when oxidized in the presence of acidified Na2Cr2O7. What will be the product when secondary alcohols are oxidized in the same conditions? Right, well, obviously it's going to be ketones. Reacts with different reagents and form different products, obviously, and some of them can be nucleophilic substitution, can be elimination. In which of the following reaction fission of bond takes place between O and H? And fission means breakage. Yep, definitely in reaction of Na, this bond is broken, and instead of an H we get an Na. Reaction with Ajax. Now Ajax can be any sort of halide like HCl or HI, and in that case usually it's the entire OH portion that is substituted. Same with PCl3 and same with SOCl2. So the answer can only be A. So which one of the following is the most reactive alcohol when bond is to be broken between the carbon and the oxygen? In this case, the one that is tertiary will be the most reactive because the resulting carbocation when tertiary is the most stable. So this is the answer. And these questions about stability and what makes the OH bond or the CO bond most easily broken, they are repeated again and again, kind of like a pet question, so to speak. So it would be suggested that you read these with the utmost care. So which of the following is an example of dihydric alcohol that has two H's? 1,2 ethane-diol. Yes, that does contain 2OH. What about this one? 1,2,3 propane-triol. That would be trihydric. 2-methyl 2-propanol, that just contains 1. And 2,2-dimethyl 1-propanol, again 1. So the answer is 1,2-ethane-diol. Now this has a common name, that is glycol. So you need to know the common name in case it ever comes up. And so glycol is a dihydric alcohol. So when excess ethanol is treated with concentrated H2SO4 at 120 degrees Celsius, what is the product that is likely to be obtained? Usually you use about 180 degrees Celsius to get an elimination, to get an ethene, and if it's less than 180, there is this other reaction that is a possibility. And so what is that reaction? That is a reaction in which you can get an ether. But if you look over here, you don't have any such option, or do you? We do in fact have an ether, ethoxyethane. So this can be the answer. Now the ethers topic is something that is not mentioned, but the naming is something that you should at least be able to do. they do often mention it, and if you are totally unfamiliar with it because we have not done ethers at A levels, you will be in for a disadvantage. So familiarness with the nomenclature of the ethers is a good idea. And the ether portion is just, I believe it's just 1 page long, and it's part of the phenol alcohol topic. So what is ethoxyethane? Ethoxyethane is diethyl ether, and what that means is that this can definitely not be the answer, because ethoxyethane will then have 4 carbons and we just had 1 carbon to begin with. So the answer is most definitely ethene, even though the conditions would suggest otherwise. Naming is important. What about dimethyl ether? That is NO with a methyl on either side, and it's called methoxymethane. What about ethyl N-propyl ether? An ethyl on one side and N-propyl on the other. Its IUPAC name is then ethoxypropane. What about methyl phenyl ether? Well, the IUPAC name is then methoxybenzene. So this familiarization with the nomenclature is something you need to do, and you don't need to know anything else from the ethers topic. So alcohols give the type of reaction when treated with halogen acid, and a halogen acid is basically, say, HCl. So with an alcohol, do you get an elimination? No. An oxidation? No. An acid base? No. A nucleophilic substitution? Yes, you can have that. Again, this is something you are familiar from A levels already. So 2,4,6 trichlorophenol is the strongest antiseptic in Dettol, and it has already been mentioned that chlorine is often used in the manufacture of antiseptics. So which of the following reagents is suitable for its preparation? So you need to realize that when we have phenol and we want to make 2,4,6 trichlorophenol, we're going to be using electrophilic substitution. So we need an electrophile. Now with Br2, it's a possibility. It can happen. You have Br2 in the aqueous format. The reaction will take place. What about PCl5, SOCl2, or even HCl? PCl5 and SOCl2 are usually used as reagents in which nucleophilic substitution is required. So I don't think it's a good idea. And HCl is largely used for, well, electrophilic stuff, but electrophilic addition, because we also have an H portion that needs to go somewhere. So Cl2 is the good option, because in general we can successfully electrophilically substitute a phenol using just Br2 in the aqueous format at room temperature. So it should theoretically be possible with chlorine as well. When Lucas reagent is treated with an alcohol and oily there appears at once, then what is the type of the alcohol? Is it tertiary alcohol? Is it neo alcohol? Is it primary? Is it secondary? The answer is tertiary. A neo alcohol is one in which the second carbon has basically 3 carbon attachments. Now neo alcohol is not necessarily tertiary, and so it does not necessarily show the appearance of an oily layer at once. There is a distinction between neo and tertiary, which some students miss out on. So again, we'll leave this for the last. So the OH group in phenol is ortho-para-directing and deactivating, meta-directing and activating, ortho and para-directing and activating, or meta-directing and deactivating. We know that OH is definitely ortho and para-directing, and what that means is that whenever it attaches to a benzene, the second and the fourth positions are the ones that are activated. But is it activating or is it sort of like deactivating? It's certainly activating, even though we would expect it to not be that way because it's electronegative. But the reason is that one of the lone pairs of the O is sort of like delocalized in the rings, and so that makes it an ortho-para directing activating group. And what about the acidic nature of phenol? The acidic nature of phenol is due to hydrogen bonding. You should know that has nothing, that is a physical property to an extent, has nothing to do with the acidic property. Is it due to the benzene ring? Unlikely. What about the phenolic group? The phenolic group is this part over here. Potentially. And D is the resonance stability of the phenolate ion. That would contribute to some extent, because if it was an unstable one, it would quickly go and take the ion again, but the problem is that it's not called the phenolate ion, it's called the phenoxide ion, generally speaking. So this one requires some research on my part. I would go with phenolic group. This is unfamiliar terms. When ethanol is oxidized by acidified K2Cr2O7, the color of the solution turns green due to what? It's because K2Cr2O7 has been reduced because it has successfully oxidized ethanol. And what is the reason? The oxidation of Cr3 plus into dichromate? No. The oxidation of dichromate? No, because it's actually the reduction. The reduction of dichromate 6. Is it in the 6 format? Yes, it's in the 6 format to plus 3. Yes. Well, there hasn't been any loss. And even if it was, the answer was because of the oxidation of ethanol, it would be wrong, because while the oxidation of ethanol is something that has happened, it's not the causation. It's not the cause for the change in color. So which of the following structural isomer is not shown by alcohols? Well, the chain isomerism is shown by literally every group, and when it contains more than 3 carbons. Functional group isomerism, it does show functional group isomerism with the ethers, but not within the group, obviously. And it can most certainly show position isomerism, and what about tautomerism? Now this is this type of isomerism that is unfamiliar to us A-level students. It's actually a bit archaic and most people don't really consider it anymore, but it's part of the syllabus, so we have to go with it. And it's something that is shown by amino acids, because it's due to the ability of the AH atom to be exchanged within the molecule, so the formation of the deuterone. But there are other compounds that show tautomerism as well. Keto-enol groups. Now this is not an alcohol, because ethanol, it's not enol. E suggests that there is a double bond in there somewhere. So which of the following structural isomerism is not shown by alcohols? That would be tautomerism, because an enol will not show tautomerism, and an enol will not show tautomerism, even though an enol will. This is important. It can show position isomerism, it can be primary, tertiary, whatever. Chain is shown by literally everything, and functional group isomerism can be shown with the ethers. And as to where this tautomerism thing comes up from the book, it's actually the first Chapter 7, Fundamental Principles of Organic Chemistry, which is on page 118. And over there, in the last part of the chapter, you will have Tautomerism. And I'll read parts of it. It's actually just one line. And this type of isomerism arises due to the shifting of protons from one atom to the other in the same molecule. That is literally the only thing that is given. This was additional information given to us that ketoenol can also show this. So this page 131 to 133 is pretty important because there was shown another type of isomerism we didn't know about, which was metamerism, in which the compounds that show metamerism, they need to be of the same homologous series, and so in this way it is distinctive from the functional group isomerism, which needs that isomers that show functional isomerism need to be of different. So like contrasting criteria for these two types of isomerism. Now if we move backwards to the top to some of the questions we left out for reasons. We'll talk about this phenolic part later. The process of fermentation, and you'd be wondering where this comes from. This is again from the alcohol chapter, the starting phase of that chapter, and page number 214. We mentioned a lot of stuff. And it's they've given in detail this sort of industrial preparation from molasses, and the fermentation process has been detailed with the name of numerous enzymes. They've told us stuff like that alcohol obtained for fermentation is only up to 12% and never exceeds 14%, and this 14% and 12% is about concentration. Right? And they've also told us that the reason they cannot go beyond that is because the enzymes, they end up sort of like dying beyond this limit, because the concentration becomes lethal beyond this limit. And that the alcohol is distilled again and again to obtain 95% alcohol. And what is that alcohol called after it has been rectified again and again and made up to 95%? That is what you call rectified alcohol. And they've also told us something called absolute alcohol. And absolute alcohol can also be obtained by the redistillation of rectified spirit in the presence of calcium oxide, which serves to absorb its moisture. So calcium oxide is a dehydrating agent which you have been introduced to. So we have three new pieces of information. And if we obtain alcohols from fermentation, their concentration does not exceed 12% to 14%, but via distillation, successive distillation, we can obtain alcohol that is up to 95%, which we call rectified spirit. And if we redistillate in the presence of calcium oxide, we get something called absolute alcohol. Now, other piece of information is that what is molasses and what is starch, because you can use either of these for fermentation processes. And molasses is a residue obtained after the crystallization of sugar from concentrated sugarcane juice, and this is called molasses, undergoes fermentation in the presence of enzymes present in yeast to give ethanol. Now molasses is C12H22O11 and the same as the formula for sucrose. We have it reacting with H2O in the presence of invertase enzyme, and this invertase enzyme has been mentioned in the chemical kinetics topic, and you get glucose and fructose, and that is the function that was mentioned in this chapter, in that chapter as well. And then we have zymes coming up, which is doing the actual fermentation, the conversion of glucose to ethanol and CO2, and zymes has also been mentioned in that topic. From starch, and starch has this functional unit, or this unit formula of C6H10O5N. Again, we are reacting it with NH2O in the presence of diastase, which has also been mentioned. So we get maltose, which has the same formula as sucrose. Then maltose is reacting with one molecule of H2O in the presence of maltase, so we get glucose, and then glucose is basically sort of like the same reaction with zymes, and we get alcohol and we get CO2. Right? So what is the actual fermentation process? The actual the actual fermentation process is the one that is catalyzed by zymes, the conversion process that results in CO2 formation. And there were these two questions I missed out initially. And ethanol is prepared on the industrial scale by the presence of fermentation, biochemical process. Optimal temperature is 25 to 35. So the first one is correct. And proper aeration is needed. C is correct. Dilution of solution is needed. And there shouldn't be any preservative present. So D is wrong one, because they've clearly mentioned the necessary conditions. Optimal temperature of 25 to 35. The solution needs to be diluted. There needs to be proper aeration, and there shouldn't be any preservative. Again, I've mentioned this has not been mentioned anywhere in the syllabus, but sometimes they do ask stuff from the book which is not in the syllabus, and A-level students are disadvantaged because they have not read that thing at all. Which is why I'm saying you should do these two as well. And which one is incorrect? Sucrose on enzymatic hydrolysis yields glucose and fructose. That is obviously correct. Starch gives sucrose. That is wrong. We have just said that starch will produce maltose. I'll represent this. They have represented starch as C6, H10, and then we have O5. And obviously this can't just be starch, this is just one unit representative of the proportion of each of the three elements. And we have N molecules of H2O because we need one for each such subunit, and there are probably multiple such subunits. And then we're going to get maltose. And we're going to get N number of maltose, which is the same as the amount of H2 we have used up, and the amount of functional units of this type that are found. And this is when we get N molecules of maltose. So obviously we're not getting sucrose, even though maltose and sucrose are actually, they are isomers of each other. Same molecular formula. Unfortunately, they have different structural formula. And yes, this one is correct. This one is correct. This one, on the other hand, is pretty false. And there was this other topic about pyridine and how we can use that occasionally, and along with other stuff that can be used for the effective denaturation. I can't seem to find that question over here. So it's also on the same page. They've written that in order to denature alcohol, you can add 10% methanol, and we call that methylated spirit. And you may also add a small quantity of pyridine or acetone. So denaturation can be obtained in a couple of different ways. So pyridine is an option, acetone is an option for denaturation, 10% methanol is an option which will make methylated spirit, but ethanol is not an option. So this page is sort of important. There is also the industrial preparation of alcohols. Again, not exactly included, but a good idea to take a cursory look at it. So, methanol was initially prepared from the distillation of wood. This is an interesting tidbit to know, which is why we may call it wood spirit. Methanol can be called wood spirit because it was at one point it was obtained from the distillation of wood. Seems pretty crazy to me. So you need to purify mixture of carbon monoxide and hydrogen, compress at 200, take into reaction chamber. Catalyst should be between 450 to 500 in temperature, and you get ethanol vapor being produced. So this is it. Then there was this last one. Fermentation, is it reversible? Fermentation is unlikely to be reversible. Is it exothermic? Is it endothermic? This has not been mentioned anywhere in the book. What do you think? Is it a process that is likely to be endothermic? I wouldn't say so, because they've said 25 to 35, which is really low temperature, and endothermic tend to need higher temperature. So exothermic is the answer, and this is something we get from reasoning. So hopefully you guys found this to be helpful. If you did, please like, subscribe, leave comments, and your